All right, good evening, everyone. So this week we need to discuss linear modeling. So this is week 10. Week 9 was the exam, so now we're on week 10. So to get started, we need to ask ourselves the question of what exactly does it mean to model something? Now, in real life, we always basically need tools to allow us to predict what will happen. And we use modeling to do this so that we don't have to guess what's going to happen, right? Basically, modeling allows us to predict things. And modeling doesn't always have to be mathematical. In a general sense, we use modeling all of the time. Many times, modeling is mathematical, though. Basically, a model will provide us, will basically reduce a scenario down to its most basic form so that then we can see what's going to happen, right? So it includes all of the different things that can change, all the different things that can affect the situation we're looking at, so that basically we can make an educated guess or estimate as to the future. So the definition of what exactly a mathematical model is basically that it's a process of using various mathematical structures, such as graphs, equations, etc., to represent real world scenarios or situations, right? And what we're going to look at, and kind of in general, the three main ways that we can represent mathematical models is using graphs, equations, right? Or what we call ordered pairs. So graphs, equations, or ordered pairs. Now, if you remember, we talked about functions kind of in the beginning of class. And basically, functions are relationships. So if you remember the black box example that we did, we kind of had a black box and we didn't know what was happening inside of the black box. And basically, we put something into the box, some input, right? Something happens inside of it, and we get out some output. And that's the basic kind of vision of what a function is. Now, in particular, for something to be called a function and not just a relationship, right, we have to have a particular kind of relationship where every input has exactly one output and only one output. Now, that idea is very important because if you imagine, the world would be confusing if there were a whole bunch of things around us where you feed in some input, right, and you get some random output. So, like, let's imagine some kind of vending machine, right? I'm going to try my best to sketch out a vending machine. And you come along and you are trying to feed your money into the vending machine. What if when you put that dollar in, which is your input, what if every time you put the dollar in, you might get something random out, or the value of the dollar might be interpreted as different? So sometimes you put the dollar in and you get out a bag of chips. Other times you put the dollar in and you get a diamond necklace. Sometimes you put the dollar in and you might just get a bottle of water, right? But you don't know what's going to happen because it's kind of just like random. It's like a slot machine. You put something in and you don't know what you're going to get, right? It's random. So that would not be considered a function. In particular, we are interested in functions, right? We're interested in functions because we can put something in and we know what we're going to get out. Now, it's very important. This says that every input has exactly one output. That does not mean, right? That does not mean that we can't have an output with more than one input. So an input has to go to exactly one output, but our outputs could have multiple different inputs, right? And if we go back to our vending machine example, you could put in $1, right? And that equals like whatever value it is for a dollar. Or you could put in what? You could put in 4 quarters, right? You could put in 2 dimes and a nickel 4 times, so 8 dimes and 4 nickels, right? And you get to $1. There are a couple of different options, a couple of different ways that you can get something that adds up to equate to $1. So with all of these different inputs, we could get the same output. But to get a bag of chips, right, there would be only to get a bag of chips, we would need $1. And our dollar, right, would only lead to the bag of chips. It wouldn't be like we could put in $1 and get a bag of chips, or get this, or get that, right? Our dollar would only lead to one output. So this will be kind of like a special vending machine, right? And basically what we want to do is we want to model the relationship between the inputs and the outputs. Now, when we do our linear modeling, right, we have what's called an independent variable and a dependent variable. Our independent variable, right, is our input. That's our independent variable. The reason why we call it an independent variable is because we have a choice over what we are going to put into our function. So we can choose, do we want to put $1 in? Do we want to put 4 quarters in? What do we want to put in? No one's going to dictate that for us. We get to choose what we put in. Now our dependent variable, that's our output. We call it dependent because it depends on what input we put into the function, right? So we can't get a random output out. Our output is based on the input. It has to be based on the input, right? So it's dependent on the input because it's based on the input. Now, you'll notice here, right, we have an X here for our independent variable. Usually, when we're looking at functions, we will usually give a general name to our input, and we'll just generally call it X, right? That's the general name for our input. And in general, if we don't have a specific name, we will in general call our output Y, right? That's what we'll generally call our output. Now, if you remember, if you go back, you'll see exactly what I'm talking about. But this is the same thing we spoke about before, where this is like the John Doe of functions, right? The John Doe. It's just a generic name. We'll call this one the Jane Doe. So if you watch crime shows, right, whenever they have a body and they don't know who the person is, they call it John Doe or Jane Doe, right? Now for the name of the function itself, we give it a generic name of F, right? That's what we give it. We call it F. Now, going back, another way we can write our output, in this way, where we basically say F of X. Now at this time, if this part is confusing, I'm kind of moving a little fast here because we did a lot of this stuff in the beginning of the semester, you can go back and look at the slides and review the slides where we actually talked about this F of X. I believe that was week 1 or week 2. Basically, we say F of X, which is basically telling us that we have a function and our input into the function is X and the name of the function is F. And we say, the way we say this is F of X. And we'll usually say equals Y. So if we take X, put it into the function F, we get out Y. Now, just one last note on the independent variable and the dependent variable, right? Basically, what we're trying to do when we're looking at functions is we're trying to see if we change one thing, and the thing that we change is something we control, how does it affect something else, right? So we change the independent variable, and we're trying to figure out how it will affect the dependent variable. We change the X. We want to figure out how it will affect the Y. So if we look here, we have a couple of little situations, right? In the first situation, right, we have this kind of relationship where we have a P as an input and the P goes to M, right? The Q goes to N and the R goes to N, right? So our P is our input, our Q is our input, and our R is our input. And we can see that this is a function because, in fact, each of these inputs only goes to one output, right? So each of these inputs, the P has one output it goes to, the Q has one output it goes to, and the R has one output that it goes to. Now, in this second scenario, we have a P, Q, and R, and our P this time is going to an X. Our Q is going to a Y, and our R is going to a Z. Now, this example is also a function because, again, when we look at our inputs, each of them only goes to one output. Now, in this last scenario, it's not a function. Why is it not a function? P goes to X, that's okay. But look at Q. Q is a toss-up. Either we could go from Q as an input and we get out Y, or we put Q in as an input and we get out Z. So either one. And it's kind of a toss-up which one we're going to get. That's what makes it not a function. We want a scenario where we put something in and we know exactly what we're going to get out. That's what we're going for. We put something in and we know exactly what we're going to get out. And here's another scenario where basically we're looking at it as basically a machine. We put some inputs in, we get some outputs out, and the box is our function. Now, in the beginning of class, when we did it, we kind of did some scenarios where we didn't know what was going on inside the box. What we're going to do now is we're going to unveil the box and basically look at a way to figure out what is actually going on inside the box. Because by knowing what's going on inside the box, that can guide us on what inputs we can put into the box, and it can guide us on what outputs we expect to get out of the box. Now, the first way that we're going to look at representing functions is basically by representing functions as ordered pairs, right? And when we represent functions as ordered pairs, we're basically pairing the inputs with the outputs. That's basically what we want to do. We want to take our inputs. Now, another name for our inputs, like we said earlier, is the domain, right? And the domain is basically all of the possible inputs, or not all of the possible inputs, because again, you can put anything you want into a function, but it's basically all of the inputs that make sense, right? That's basically what the domain is. All of the inputs that make sense, right? And that's kind of key. Imagine your computer, right? Imagine your computer. I mean, there are different things you can do. You have a whole keyboard. You can press buttons on your keyboard. You can turn it on, turn it off, and each of those buttons does a thing, right? And ideally, that's what we would do. We would just push the buttons. But if we wanted, we could pour water on the keyboard and look at that as an input. That doesn't make no sense to pour water onto your computer. So we wouldn't say that water was in the domain of possible inputs for a computer. Now, the range, on the other hand, the range is all possible outputs. Now, again, because our outputs, right? Because our outputs are dependent on the inputs, we can definitively say that with all of our inputs, these are the only possible things that we can get out, right? Because when we say we know we can put this in, we know we can put this in, we know we can put this in, we can also say that we can only get these couple of things out, right? So that's what the range is. The range is basically the set of all possible outputs while the domain is the set of all inputs that make sense, right? And it's an inclusive set. It includes all of the possible inputs or all of the possible outputs. Now, to write our functions as ordered pairs, basically what we want to do is we want to write it like this, where we just kind of list out, here are the x's, here are the y's, or here are the inputs, and here are the possible outputs. Now, another way that you'll see this written, right, usually actually how you'll see it written, is you'll see it written in this form, x comma y, where the x is the input and the y is the output. And this is what we call basically an ordered pair. And if we wanted to write the rest of them, see that here, the 2 is the input. What's the output? 6. So we could write 2 comma 6. That's an ordered pair. It's basically telling us that 2 goes with 6. If we put in 2 into the function, we'll get out 6 from the function. We also have 5 comma 15, which basically tells us if we put in 5, we'll get out 15. We have 10 comma 30, where it's saying if we put in 10, we will get out 30, right? And that's basically the domain and range, and this is the way we write it. This is the general way that we want to write it, like this, where we write out our ordered pairs. Now, another way we can represent functions is through a graph. And what you'll see here is this is basically a graph. Now, you should have some exposure with graphing. I'll send some material as like a review or a touch-up if you don't remember all the details for graphing. But just in short, what we'll do is I'll just explain it briefly. So we have 2 axes, right? The x-axis, which is this line that goes across here. And we draw the arrows on the end because it can go on and on and on until infinity. And we have the y-axis, which is this line going up or down. On our x-axis, we write down the inputs. That's where we measure the inputs. On our y-axis, going up, is where we measure the outputs, right? And then we just basically make points at the places where the inputs and the outputs intersect. So here we have 1 point. And what's our 1 point? Our 1 point is 0, comma 0, right? That's our 1 point, 0, comma 0. Where would that be? That's an input of 0 and an output of 0. The next point we have is what? 1, comma 2, right? That's an input of 1 and an output of 2. So what do? It's like we started here and we marched over 1 space to right here. And then when we were here, we marched up 1, 2 spaces to get to this point here. Right? Same thing here. We march over 1, 2 spaces, and we march up 1, 2, 3, 4 spaces. So that's how we got 2, comma 4. Here it's the same thing. We're going over and up, and it's 3, comma 6. And here it's the same thing. We're going over and up to get 4, comma 8, or an input of 4 and an output of 8. So we can graph any point, right? Any ordered pair that we want or point that we want by using this method of just inputs and outputs. And the inputs being the x-axis, that's what we call it. And we graph the outputs on the y-axis, that's what we call it. So let's try to find a couple other points. What if we wanted to find a point that was -4, -6? Well, what will we do? We're here. First, we're going negative, so we're going this way, right? And we walk over until we get to our input place. Here is our input place right here. and then we go down until we get to our output. We said, what was our ordered pair? Our ordered pair was -4, comma, -6, right? So we're at 4. We march down to -6, and we get this point right here. You don't have to draw the lines. I find drawing the lines to be helpful, especially when you start off, because it's just giving you an idea to make sure you're in the right place. What if we wanted to graph something like 8, 4? Right? What if we wanted to graph this thing? 8, comma, 4. First, our input is 8, or our x value is 8, and our output, or our y value, is 4. So we march over to 8, that's right here, and then we march up until we get to 4, which is right here, and we get to this point right here. What I want you to do is go back like a couple of seconds in the video to the point where I hadn't drawn anything, and just try to plot a couple of points, right? So you can try to plot 6, comma, 6. Try to plot -8, comma, 3. Try to plot -6, comma, -2. And for the last one, I want you to try to plot -2, 8. So just pause the video, try to plot it. So 6, comma, 6 would be going over the 6 and up to 6. So over for our input and up, right? -8, comma, 3. And I'm sorry, you should have paused the video a second ago because I'm going through the answers now. -8, comma, 3. When you plot it, you could just write the point 6, comma, 6. -8 and 3 would be going over to -8 and up to 3, which is in between 2 and 4. So we'd be about right here. And this would be -8, comma, 3. And then we have -6, -2, which will be going all the way over to -6 for our x value, and then going down to -2 for our y value, which will put us right here, which would be -6, comma, -2. And lastly, we have -2, comma, 8, which would be going over to -2 right here, and then going up to 8 right here. Let me draw our little point. So -2, comma, 8. You can try to make your own up, try to graph a couple just to get practice. It's good practice to just practice graphing some points, right? If you were at all unsure. So moving on, what we need to understand now is this idea of linearity. So again, this section was called linear modeling, right? Now, when we talk about a linear model or a linear function, what we're basically saying is that the change between our input, or our independent variable, and our output, or our dependent variable, right, is some form of multiplication. Where basically our output is some multiple of our input, right? So we multiply the output by something, and that gives us the input. I'm sorry, we multiply our input by something, and that gives us the output. The multiple, right, whatever we're multiplying by, right, the multiple, we call that the slope, right? That's what we call the multiple. So whatever we multiply by to get the output is what we call the slope. And we can find the slope by dividing the rise over the run. Well, the way it looks is like this. Rise over run. The rise is how far up we go, while the run is how far over. So how far up divided by how far over, right, to the left or right. Now, when we go up, that could also be going down. And going over could be going left or going right. So our slope could be a negative number if we're going down to get from one point to the next point. Right? Now, there are two scenarios, basically. One scenario we can have is where we have what's called the starting point. And if our starting point is 0, right? If our starting point is 0, then the input is simply a multiple. The output will simply be a multiple of the input. But if our starting point is not 0, so when our starting point is not 0, right? Our output is going to be a multiple of the input plus whatever the starting point is. So it'll be the multiple of the input plus the starting point. Now, what we do is we can call the starting point, which is basically a point we start if we don't start at 0. We can call that the y-intercept, right? And that's because that's basically the value of the output when our input is 0. And we call the slope m, and we call the y-intercept b. And those are a little bit more than just general names, because almost always that's what you'll see, that the slope is called m and the output is called b, right? I'm not the output. The y-intercept is called b. So the slope is m, the y-intercept is b. So let's say that one more time. The y-intercept is basically the value of the output when our input is 0, meaning we put nothing in. What do we end up with? So let's look at an example really quickly. Let's say we work at a store, right, and we get commission, some form of commission. Y'all gonna have to excuse my spelling. So let's say we get some form of commission. Let's say we work maybe at a shoe store, and what they say is that for every pair, it's a fancy shoe store. So for every pair of shoes that you sell, right? For every pair of shoes you sell, they say we're going to give you $250. You get $250 commission, right? So for every pair of shoes you sell, you get $250 commission, right? Now, what we want to do is we want to find out, basically, how much money we would have if we started off with no money. Right? How much money if we start with no money? And we want to find how much money we'll have if we start with $200. So if we start, so we already have $200 in the bank. We want to find out how much money we'll have. So for both of these examples, we'll say that we sell on average, let's say we sell on average 20 pairs of shoes each month. 20 pairs each month, right? So what we want to find out is how much money will we have if we sold our 20 pairs of shoes? How much money are we going to have? So if we look at that, right, what can we do? Well, in the first scenario, it's kind of pretty simple, because actually I want you to pause it. Pause the video here and try to solve it yourself, right? Pause the video, solve it yourself, and then come back to the video, right? So for A, you can start the video now if you unpaused it. If you paused it, we're going to do the answer. If you didn't try to solve it yourself, pause it and try to solve it. So for A, right, what are we going to start with? What do we always start with when we solve problems? We always start with a find, right? I'm going to actually change the color so that y'all can see that we're doing a solution. So for A, right, the find is what? The amount of money. So that's the find for A. What amount of money are we going to have, right? That's just generally what we're trying to find. So the given here is that we get what? $250 per pair of shoes, right? That's what we get. $250 per pair of shoes. And another thing that we're given is we ain't got no money in our bank account. And we currently are what? Starting with $0. So we go back to our slides. What's it say? If the starting point is 0, the output will be a multiple of the input. So what are we going to multiply our input by here? Well, what's our input? In this scenario, our input, and that's what we're going to write in our given, our input is what? 20 pairs of shoes. That's what we can control, because you can't control, you're not going to go to the company and be like, give me a different pair of money. We can control the number of pairs of shoes. And you're not going to be able to come to the company and say, I don't care how many shoes I sold. I just want you to give me this much money, right? So our input is 20 pairs of shoes. We're trying to find our output. So what's our output? Now again, the slope is basically what you multiply your input by to get the output. That's what the slope is. What do we multiply our input by to get the output? And if you think about it, we're going to multiply our input by what? $250. We're going to multiply our input by $250, right? So what do we need to do now? So we've done the find, we've done the given, right? What do we need to do now? Now, all that's left is to do the solution. So we do our solution, and you probably already figured it out. But basically, the amount of money we make is going to equal, right? The amount of money, our money, is going to equal the 20 pairs of shoes that we sold times the $250 we get in commission. So what's 20 times 250? 20 times 250 is 5,000. Right? So in that month, we'll make $5,000 in commission. Right? 20 times. So do that in your calculator if you couldn't do it in your head. Right? We get $5,000 in commission. That was relatively simple. There was nothing to add because we don't get any money, right? We don't have anything, right? We didn't start with anything. Now let's do the second part. So for the second part, what's the main thing? Well, our find didn't change, right? We didn't change our find. Our given changed a little bit. We still are getting the $250 per shoes, right? Our input is still 20 pairs of shoes. Our slope, or what we multiply by, is still $250. But what's changing? What's changing is our starting point. So for this one, I'm just going to write the given. The given here, instead of starting with what? Instead of starting with $0 in our bank account, what are we starting with? We're starting with $200. So this time we start with $200. Now if we go back, well, we'll see that if the starting point is not 0, then the output will be a multiple of the input plus, keyword plus, whatever the starting point is. So to find our money in this case, what do we need to do? Well, we're going to do the same 20 times 250, But this time we're starting with something, so we need to add in what we start with. And what do we end up with? Well, we do the multiplication first because it's PEMDAS. We get 5,000 plus 200, which equals $5,200 that we would make in that month. So you can see the two different scenarios, right? Either our starting point is 0 or our y-intercept is 0, or our starting point is $200, and in that case, we can multiply by the 250 and then add the $200 in there. So that's our first example. Let's go back to our slides, right? And again, I want you to remember, we call the slope what? We call it M. And we call the y-intercept what? We call it B. So when we look at our slopes, we can have a couple of different scenarios. So the first scenario we can have is what we call a positive slope, where M is greater than 0. For a positive slope, it's exactly what it looks like. We're basically, our line is trending up as we walk on it from left to right, right? Our line goes up as we walk from left to right. So basically, if we walk from left to right, we'll be going uphill. That means we have a positive slope. So you should be able to look at a picture of a graph with a straight line and say whether or not the slope is positive. The next thing we can have is a negative slope. And a negative slope is basically a scenario where M is less than 0, right? Where M is less than 0, our slope is negative. And what that means is that our line, instead of trending upward, our line is trending downward. So if you start on the left side and you march, right? If you start on the left side and you march, you're going to be going downwards as you go from left to right. Now, another case might be if we have a 0 slope. So this would basically be M equals 0. And when the slope is 0, you're not going up, you're not going down, right? You're not going up, you're not going down. So what are you doing? You just stay exactly in a straight line where you are. So you walk from left to right, and you stay in a straight line. And that's a 0 slope. And the last scenario we can have is an undefined slope. Now, for an undefined slope, it's basically saying that when we start going from left to right, we don't go anywhere, right? So for the 0 slope, when we went from left to right, we stayed in a straight line. We had the same output for every input as we went from left to right. But in an undefined slope, right, for a given input, right, our output does not change. And what do we say we need for a function? For a function, every input has what? Only one output. And it's exactly one output. Every input has only one output, right? That's for an undefined slope. Now, to find the slope, we need to basically do rise over run, right? And it's a rise or a fall over the run. So how far up we go divided by how far over we go. So if we look at a scenario, a new example, let's say we start at this point here, right? Let's say we start at the point 3, 7, and we end up at the point 9, 15, right? So we start at the point 3, 7, and we end up at the point 9, 15. Well, we can do rise over run. Here is our x value, right? We can call this x1. We can call this x2. Here's our y value. We can call that y1. y2, right? And what we can do is we can find the slope by doing the rise over the run. So I want you to pause it, and I want you to try to figure out what the rise over the run is. That's what I want you to try to figure out. Pause it and try to figure it out. So if we look here, we could graph it. I'm just going to sketch a graph. Go ahead. If you didn't pause it, unpause it. Here is our x. Here is our y. So our first point will be 3, 7. So I'm going to put a point here. It's like 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. And our next point, I'm just going to put it up here. I don't know if I have enough space. Is 9, 15. That's our next point. 9. So this is 3, 7. This is 9, 15. So we need to say how far over did we go? How far up did we go? So to get from 3, which is this value here, to 9, which is that value here, how far over did we have to go? Well, we had to go 6 spaces over. And to get from 7, right, up here to 15, how far up did we have to go? Well, we just do 15 minus 7. And what do we get? 8. So we went up 8 and we went over 6. So our rise over run is equal to what? 8 over 6. And we can reduce this down by dividing both of them by 3. And we get 4 over 3. Right? That's what we end up getting, 4 over 3. Now, an important note here is that the slope is basically telling us how steep our line is. Right? That's what the slope is basically telling us. So here's the line from here to here. All we need is 2 points to make a line. Right? We just need 2 points to make a line. And we get that line there. And the slope tells us how steep the line is. So a bigger slope equals a more steep line. While a smaller slope is a less steep line. Now, if you're just talking about how steep the line is, right, I want you to ignore the sign when you compare the size of the slopes, right? I want you to ignore the sign. So for example, if we look at two slopes, let's say we looked at a slope that was -6 for one line and a slope that was 3 for another line, even though -6 is smaller than -3, this line is more steep because if we ignore the negative part, we can see that 6 is bigger than 3. So we just look at the number, not the sign, when we're comparing how steep the lines are. Right, we're just looking at the number, not the sign. Let's go back to the slides. Now, what we want to really get to, so we talked about 2 ways. We talked about graphing lines, graphing functions. We talked about writing functions as ordered pairs. What we really want to get to is we want to get to the ability to basically be able to write what we call an equation for a linear function. Now, what an equation lets us do is an equation lets us basically plug in any value for an input and easily find the output. If we had to go through graphing it every time, right? Or counting it up each time. That would be very inconvenient. So we use an equation as basically a quick way to find the input and the output. That's what we look at as an equation as. To find the output, I'm sorry. We choose the input and we find the output. Now, if we already know these two pieces of information for a line, the starting point and the slope, right? It's very easy for us to write the equation because we can just write the equation in this form. This is what we call the general form of the equation of a line. That's what we call this. Y equals mx plus b. This is the general form of an equation for a line or a linear function. General form, right, for the equation of a line. And basically what that's saying is that our output is going to equal the slope times the input plus our starting point, right? And this is specifically for a line or a linear function. And if we go back to our first example we did, and we look here, isn't that kind of what we did here, right? Didn't we kind of say that we have our slope? Didn't we say that we have our slope, right? Our slope was what? 250 times our input. What was our input? 20 plus whatever we start with. In that example, what did we start with? We started with 200. So we can see that it does look the same, right? I kind of went back there. It does look the same. So for that example, we could write the equation of a line, of that line for our money example. We could write the equation of the line. It would basically be y equals, what was our slope? Our slope was 250 because that's how much we make for each pair of shoes, times, well, in this case, since we're making a general form, we're not going to put a number in there. We're just going to put x to represent our input. And this will allow us to find what we make for any number of shoes. Let's say 1 month we sell only 10 shoes, or 1 month we sell 0 shoes, or 1 month we sell 100 shoes. It'll let us find what we get for our output. And for that second example, let's not forget what we started with. Our bank account, we said, already had $20. So we say plus 20, right? So we have y equals 250 times x plus 20. And then what this lets us do, this is powerful, because for any amount of shoes we sell in this case, we could say x equals 5, x equals 0, x equals 3. We could say, what about when x equals 20? If we did x equals 20, we would get the same thing we got in that example we did. What if we did x equals 100, right? And then we can figure out how much money we'll make for any pair of shoes that we sell. We don't have to wait for our paycheck. A lot of times that's what people do. People just wait and just trust whatever somebody says. So if anybody's ever worked commission, right, then you've probably done something like this. And if you haven't, you've probably been one of the people that's just like, I don't know how much I'm going to make this month, but I sold like 12 shoes or whatever, or 12 cars, or whatever kind of commission you whatever store you're working at. So I'll probably make this much. If you had this equation, right, you could find out what you would make for any amount of whatever it is that you're selling, for any amount. So that's what it lets us do. It lets us find outputs for any input that we choose. We could pick 2,000, right? And we would still be able to find the output for if we sold 2,000 shoes. So now we need to look at finding the equation of a line or a linear function. Excuse me. If we do not know the starting point and the slope. So if we don't know the starting point and the slope, then what can we do? Right? So that's what we need to figure out. What do we do when we don't know the starting point and the slope? So we have two options. When we don't know the starting point and the slope, right, we have to either know the slope and a point on the line, or we have to know 2 points on the line. Now, both of these methods are not all that complicated. They're actually pretty simple. And the second one is just one extra step beyond what we have to do for the first one. So as long as we have those two pieces of information, we can find the equation of a line, and we can write it in this form, which is, again, the general format for the equation of a linear function, right? And our linear functions always make lines. So to start off, if we know the slope and a point on the line, so we know the slope, right, and we know a point on the line, then here are 4 steps that we do to try to find the general form of the equation. And again, we want something in the form of y equals mx plus b. That's what we want, right? So let's do an example. Let's say we have the slope. Let's say we have the slope m equals, say, -5, and we have 1 point on the line. Let's say our 1 point on the line is 2, 10. So we know the slope, and we have a point on the line. So the question is, what do we need to do? So let's follow our steps. So step 1 says write out the slope, right? Write out the slope and the point that you know. So we've already done that. We wrote it. So now we can work with it. That's the first step, just so that we can be clear what we're working with. We want to write out the slope and the point. Step 2 says plug those values into the equation y equals mx plus b. Plug x and y values for the y value in the equation. That should actually say for the x or y value. I'll leave out the x value. So for the x or y value that you know in the equation. And then plug the slope in for m in the equation. So let's do that. First, let's write y equals mx plus b, right? And what we're going to do is we are going to plug the things that we know in. So our slope gives us m, and our point gives us x and y, right? Remember, this is the x, this is the y. So we know y, right? We know y. We know m. We know x. So what is it that we don't know? We don't know b. And so the whole purpose of this method, right, is to find out what b is. And once we know b, we can rewrite the general form. Now, just real quick before we continue, what did we say b was? When we said the names of different things in our function, what did we say b was? So just think about that for a second. What did we say? Look back in the notes if you have to, and I'll tell you the answer. We said b was the y intercept, right? That's b. B is the y intercept, or what y equals when what is 0? When x is 0. So we need to know the y-intercept to be able to write the equation of a line. So let's go back to, so we did step 1, right? And let's actually plug it in. When we plug it in, we plugged in 10 for y equals, we plug in -5 for x, and we plug in, I'm sorry, not -5 for x. -5 is in m, the slope. -5 is the slope. So we plug in -5 for the slope. We plug in 2 for x, because that's what x is, plus b. And we leave b as blank because we don't know what it is. That's what we're trying to find out. So going back, the next thing we need to do, step 3, is step 3 is that we need to solve the equation for the y-intercept, right? Or we need to solve for b, right? That's what we need to do for step 3. So in order to solve for b, we use what's called basically reverse PEMDAS method. And now the reverse PEMDAS method is basically doing PEMDAS in reverse, right? To isolate that b. So first, let's simplify this. By simplify, I just mean multiply all the stuff that can be multiplied. So we're going to multiply it out. 10 equals -5 times 2 is what? -10 plus b. Now that we have 10 equals -10 plus b, we can go ahead and solve for b. So the first thing we want to do is we want to get the b by itself. So we look at what's been done to the b. So we took -10, we added that to b, so we need to subtract that -10 from b. And subtracting a negative is the same as adding it. So to undo that -10, what we're going to do is add 10 to both sides. -10 plus 10, right? And then since we do something on one side, we need to do the other side. So we add it to both sides. On the left side, we get 20. On the right side, -10 plus 10 is what? 0. And then our plus b didn't change. So now we basically have our answer, because anything plus 0 is the same number. So we can just write that as b. So now we have 20 equals b. So now we've solved for b. That was step 3. And then step 4, now that we know m and b, we can rewrite the general form of the equation, where we just, some technical difficulty here, where we just need to plug in m and b, right? That's the only thing we need to plug in. So let's go back to our example. So we have m up here already, that's m, and we have b that we just found. So now we can write the general form of the equation. I'll do that in blue. Y equals, what's m? -5 times x plus, and what is b? 20, right? So it's just those 4 steps, and that's all we need to do. So let's go to the next part, right? The next part is, what if we have 2 points? If we just know 2 points on the line, then what do we need to do? So I think I have enough space here, so I'll just do this example right here. So if we just know 2 points on the line, what we first need to do is find the slope, right? And then once we know the slope, we'll know 2 points and the slope. So it'll be just like this method, except instead of knowing 1 point, we'll know 2 points. So let's do that. Let's get 2 points on a line. Now, the reason why we can do it with 2 points is because to make up a line, all you really need is 2 points. So like if I put 1 point right here, anywhere on the paper that I put the second point, it will make a line. It doesn't matter where I put it. I could put the next second point right here. And look, straight line between the two, right? Doesn't matter. So if I have any 2 points, 2 points make up a line. I could put a point here, and I could put the second point over here, and I still get a line between the two, right? So that's why we can do this when we have 2 points. So for this example, let's say our first point is 3, 7, and our second point that we know on the line is 8, 12, right? So we have our xy for the first point, we have our xy for the second point. So what we need to do is first find the slope, So to find the slope, what do we need to do? Rise over run, or y2 minus y1 divided by x2 minus x1. Right, so we subtract the y's, we subtract the x's. The important thing is whatever we start with, we got to do that on the bottom. So if we start with y2 on the top, we got to start with x2 on the bottom, right? So this would be x1, y1, x2, y2. All that 2 and 1 represents is just which point we're looking at. This is our first point. This is our second point. So let's find the slope. So m is going to equal the slope, which is y2 minus y1. So we have 12, which is y2, minus y1, which is 7, divided by 8, which is x2, minus 3, which is x1. And at the top, we get what? 5. In the bottom, what do we get? 5. And we do 5 divided by 5, and what do we get? 1. So now we know our slope, but we need to write it in this form. Y equals mx plus b. So we know this, and because we have points on the line, we can know an x and a y that go on the line. And we still need to find b. So let's find b. Do a little squiggly here. Now to find b, we do the exact same thing we did in the previous step, see? So now that you know the slope and the point of the line, complete the steps from the previous step. Well, step 2, so write out the slope and the point of the line. So that's step 1. Let's do that. So we have m equals 1. And our point, we can use either point that we want. I'll use 3 and 7. Didn't matter which one we use, right? Then we have step 2, plug those values into y equals mx plus b. So when we plug those values in, what do we get? We have y, we're going to plug in the 7. So let's write it out. Y equals mx plus b. The 7 is going to plug in for y. The 3 is going to plug in for x. And the 1 is going to plug in for m. So now what do? We have 7 equals 1 times 3 plus b, right? And we do the process the exact same way. So we're going to start by simplifying. 7 equals 3 plus b. Then we're going to try to get the b by itself. So we're going to subtract 3 from both sides. Subtract 3. We get 4 on that side. We write out equal sign. We get 0 on this side plus b. And then from there, that 0 just goes away because b plus 0 is just b. And we get that 4 equals b. So now, what do we know? Now, we know b and we know m. And because we know b and m, we can rewrite the equation of our line, which is this thing over here. And we just write it. Y equals, what was m? M was 1 x plus 4. And just like that, we're done. That's the equation of that line, right? So we're going to do one example where we kind of just walk through the entire process from like a word problem type of scenario. So that's what we're going to do now. I'm going to go back over here. Give you a scenario, and we're going to walk through the entire process. So what can we do in this example? So let's say we start a business cutting grass, right? We start a business cutting grass, and we plan on charging $35 per lawn, right? We plan on charging $35 per lawn. Our equipment, so we got to pay something for equipment. It's not free. So our equipment, right, costs let's do $289, right? And let's say it allows us to cut unlimited lawns, right? So it's a one-time cost for equipment. So the first question is, we need to write a linear model to represent we want to represent the money we make. Represent the money we make. Right, so that's step one that we want to do. The second thing that we want to do is, what is our break-even point? And the break-even point is basically the point where the amount of money you've made equals the amount of cost that you had to put in. So our 289 is a one-time cost. We don't have to keep paying that. It's just a one-time cost we pay in the beginning. It's a setup cost. So now here's the question. What do we start with? So you pause the video and try to work through this on your own. Try to write that linear model or linear equation to represent this function, and try to work through it on your own. So what we are going to do, like always, we are going to start with what? We always start with the find. Right? We always start with the find. Always. Now, once we start with the find, what are we trying to find? So, A, we need to do a model, right? And in this case, the model we want is an equation, right? And B, we want to find the break-even point. But let's dig a little deeper into what that means. Right? Basically, in this case, the break-even point will basically be like not our starting point, but basically the place where the amount of money we make is zero. Because if you look here, when we first start, we're not at zero. What are we at? We're at minus 289, right? Because we spent money. We haven't made any money. We're at minus 289. So our break-even point is basically going to be the point where we net $0, or our output equals 0, right? That's going to be our break-even point. So now we need to go ahead and write out our given. So the first thing we know, if we go through this problem, is we see this thing, $35 per lawn. Now I'm going to give you a clue. Anytime you see something like $35 per lawn or such and such amount per this, that usually is pointing you to the slope. Now it may need to be something that you do first before you just say, okay, this is the slope. But in general, this is going to point you to the slope, because what's going to be the thing that's changing? Well, let's start off by writing our independent variable. So our independent variable, and then this will kind of give you a clue as to why that's going to be the slope. Our independent variable, or the thing we can control, is going to be what? the number of lawns. Number of lawns, right? That's going to be our independent variable. Because, I mean, we could go out and cut no lawns, or we could go out and cut 50 lawns. It's completely and totally up to us. Our dependent variable, right? I can't spell. Dependent variable, right? Our dependent variable is going to be what? The amount of money we make. Because the amount of money we make is going to depend directly on how many lawns we cut. Now the slope is going to give us the relationship between the independent and the dependent variables, right? So if we look here, we can see that this $35 per lawn gives us the relationship. That's telling us how much money we make for every lawn that we cut. So if we know we cut such and such many lawns, it's clear we're going to need that number to figure out how much money we make. Almost like as if this was a unit conversion, right? So the 35 per lawn relates these two things. It relates the number of lawns that we cut with the amount of money we make. And whenever we have that relationship between our independent variable and our dependent variable, we know that that is going to be our slope. So in this case, the problem is giving us that our slope is 35. That's our slope because it's $35 per one lawn, right? So if we're counting how many lawns we make, we know how much we're making for each lawn. Now, what else does the problem tell us? Well, the problem gives us this. Our equipment costs $289. So that's basically going to be our starting point, right? So what's our starting point? What do we call our starting point? We call our starting point the y-intercept. So let me write this. This is the slope. And our y-intercept, or b, is what? Is it going to be 289 or minus 289? Yeah, it's going to be minus 289. Why? Because that's money we spent. That's not money we made. That's money we're in the hole. And that is our y-intercept. Now, we have our slope. We have our y-intercept. We can go down here to solution, right? So for the solution, for part A, well, that's easy. We know our slope, which is 35. We know our y-intercept, which is negative 289. And what can we do? Well, if we go back here, it says if we know the starting point and the slope, then we can just write out y equals mx plus b. So let's just do that. Y equals mx plus b. And then we need to plug in m and b. So we get y equals 35x plus negative 289, right? And this is our linear model, because we can plug in any number we want for x. What's x going to represent? Well, it's our independent variable. What do we say our independent variable was? Our independent variable is what? The number of lawns that we cut. So if we plug in any number we want for the number of lawns we cut, it will get us out what? Our dependent variable. What do we say our dependent variable was? The amount of money that we make, right? So this will be our money. And this lets us map out and see how many lawns do we cut, how much money do we make. And this minus 289 is our starting point, right? That's where we start. We started in the negative. So now we can do B. And what was B? B was, what is our break-even point? So basically it's saying, what X gives us a Y equal to 0? Or how many lawns get us to 0 money? Or basically, how many lawns pay for our equipment? That's basically what we're asking. How many lawns pay for our equipment, right? And well, we can do that pretty easily. We just write out our linear model. Y equals 35x minus plus negative 289, right? And we want to know what X we get when Y equals 0. So we can do just that. We're going to plug in 0 for Y. And we're going to solve for X. Plug in 0 for Y. We solve for X. All right. So the first thing we need to do is, like, again, it's basically just reverse PEMDAS. Now you may need to practice solving these simpler equations. You may need to practice that. If you need practice, just let me know and I'll give you some practice work or send some videos that can help you with that. So the first thing we're going to do is we need to start working backwards. So PEMDAS is parentheses, exponent, multiplication, division, addition, subtraction. So we're going to start with the addition, subtraction, and undo that. So to undo addition, we have addition here. We want to undo the addition. We're going to undo it with subtraction. So we're going to do minus 289. And we're going to do that to both sides, right? On this side, we get 289 equals 35x. That part didn't change. Plus negative 289 minus negative 289. That's 0. So this is what we end up getting. That 0 goes away, so we just have 289 equals 35x. Now we need to undo this multiplication on the x, right? So we have 35 times x. To undo that, we divide. So we do divided by 35, divided by 35. On this side, the 35 over 35 cancels out. The 35 cancels with the 35, and we're just left with x. And we get 289 over 35 equals x. So what does x equal? Well, pull out your calculator and do it. What's 289 divided by 35? We get 8.26, right? 8.26 is what we get. Now, obviously, we can't cut 8.26 lawns. And if we cut 8 lawns, we'll be a little bit off, a little bit below. We need to get exactly to 0 or at 0 or above 0. So we need to cut a total of 9 lawns. And we'll make all of our money back. That's our break-even point. Our break-even point is 9 lawns. So with that, we are done for today. Don't forget to practice these problems and try them yourselves. Don't forget to pause the video where I say pause the video and try the problem before I do it. That's essential because that's what's really going to allow you to get good practice in. Let me know if you have any questions. Feel free to email me if you have any questions. Have a good night.